Okay, everybody. Sorry I'm out another day. I'll explain more as when I'm able to get back into school. I'm not sure if it'll be this coming Tuesday or not. It all depends on how my son's doing and how my wife is doing. They're still in the hospital. But I want to take a few minutes and give you something to think about while I'm gone. Our next big unit is going to be about waves. Now, waves are a very interesting subject because they deal a lot with the transfer of energy. Now, there's different ways you can transfer energy. There's different kinds of waves. There's different things you can do to get the energy from one place to the next. Now, the first thought is, what is really energy? Now, energy is an object's ability to do work to something. Okay, now what does that even mean? Now, to do work to something is to be able to apply force over a distance and to cause some kind of change. Okay, if you do work on an object, you are going to move it over a distance because you're forcing that to happen. Okay, so waves take energy from one place to the next, and then they have the ability to do work on objects and medium and materials as they go. Okay, now you can see on the screen here what you would typically think of as a wave. Now this is another topic we'll discuss later. This is actually an example of constructive and destructive interference. You see a yellow and a white wave passing over each other, and when they meet up, you see the purple one get very large, and when they kind of uh, balance each other out, you see that it kind of almost blanks out. Okay, we'll get to that another time. Right now, we just need to get some basic ideas down behind what waves really are. Okay, now there's really three main types of waves. We're really only going to study the first two, but I thought it was important to at least help you understand that there are three. Okay, now the first type of waves is called mechanical waves. Mechanical waves are any kind of wave that require a medium to travel through. Okay, now a medium is some kind of material, whether it's water or air or rock, okay, or string or something like that. Mechanical waves must have something to travel through. Okay, without it, they won't occur. Okay, because they actually use that material that they travel through, that medium, to vibrate. Okay, now all waves come from a vibrating source. We'll talk about that specifically the next time I see you. That's something I really need to explain in person with diagrams on the board and things like that. But for right now, we'll just get back to this. So mechanical waves are things like sound. Like you have to have air in the room in order for a sound wave to travel through it. Okay, you have to have water, obviously, to have a water wave. You have to have rock or something like that in order for an earthquake actually to pass. An earthquake is actually considered a wave. Okay, and obviously you have to have a guitar string to actually have the wave pass through the string. Okay, so that's the first main type, mechanical waves. All right, sound is probably the best example of mechanical wave. All right, the next group or category is electromagnetic. Now, electromagnetic is slightly different. They are the result of a vibrating charged particle, like an electron or a proton, which a lot of you sophomores are learning about right now in chemistry. Okay, we'll get more specific about that. But an electromagnetic wave is actually caused by the release of energy from a vibrating charge, typically an electron. Now, those all come from what's called the electromagnetic spectrum. I think you should probably take a moment and Google it and look it up. You could probably find a good image of it somewhere. Okay, now try and go to websites that either have .edu on them or .gov, more reputable ones. Okay, you'll get better information from them. Now those are typically X-rays, microwaves, gamma rays, visible light, infrared, ultraviolet, and radio. Okay, now those are all the result of a vibrating charge. Pretty much they're going to be an electron. Okay, typically they are always an electron. Now the difference between mechanical waves and electromagnetic waves are electromagnetic waves do not require a medium to travel through. Okay, make sure you make that very clear in your notes that mechanical waves and electromagnetic are sometimes referred to as EM waves. EM waves do not require a medium to travel through, and mechanical waves do. Okay, that's, for example, why we get all those types of electromagnetic waves from the sun in the form of radiation. Okay, we get X-rays, micro, gamma, radio. We get all of them. If they required some medium like air to travel through, we would never get them because there is none of that in space, in outer space, above the Earth's atmosphere. Okay, so we'll talk more about what really causes them later, as I said before, but um, they do not need that. Okay, those are also, to be more technical about it, are the result of oscillating magnetic and electric fields. That's something that you really won't understand until you take IB physics, which you all will. Okay, you all take that with me, but that's just another little thing. Again, I would suggest that you go on, once you're done looking at this quick screencast, you look up mechanical waves, look up electromagnetic, and be careful about where you get your information from. Okay, look in the textbook in the wave chapter and see if you can find out anything more interesting about it, because you are going to be expected to know what the different types of waves are and properties of them. The third one is matter waves. Now that's something that's a little more technical, not something we really need to get into. That gets into some, some crazy quantum mechanics, and it deals with how electrons really are waves and not really particles, and particles are really waves at the same time. It's kind of complicated. It's not something that we really can get into this year, because you have to understand a lot more about waves and energy first in order to really get a good grip on that. Plus the math is pretty nasty, and we just don't have time for that. Okay, so we're going to focus on the first two, mechanical and electromagnetic. Now there are two wave forms that you typically see. The first one is called a transverse wave. A transverse wave is what you would typically envision a wave as in your head. Okay, it's kind of what a water wave looks like, or a sine or cosine wave for you guys that are taking math analysis. You'll see that very shortly. Now, if you look at it, the wave is passing from left to right. All right, so transverse waves, it passes, not always left to right, but let's say it's passing left to right. If you notice, the little rings in the slinky that's moving are going up and down. Okay, so the key point to I'll show you the velocities going to the right, is that the particles that the wave are traveling through, basically the slinky, are moving up and down while the wave itself is moving from left to right. Okay, that's what a transverse wave does. The particles move perpendicular to the wave. Okay, and if you notice, they're not traveling all the way across. You don't see the particles all the way on the left side move all the way over to the right side. Okay, they just move up and down. They stay in one place. Now the other one is a longitudinal wave. Now the difference, as you can see then in that slinky or spring, is that longitudinal waves, the particles kind of bounce back and forth, but they bounce back and forth in line with the movement of the wave. So the wave is moving from left to right, okay, as you can see on the screen, and the rings of that slinky are bouncing in that same line. Okay, they're bouncing left and right. Okay, so longitudinal waves, the particles move parallel to the direction the wave moves. Transverse waves move perpendicular to the direction the wave moves, as you can see in this little video. Okay, it's just showing particle movement. Okay, but that's a key idea. Now, a good example of a transverse wave is visible light. Okay, the light that you use to see is transverse waves. Okay, a good example of a longitudinal wave is typically a sound wave. Okay, like as the sound is coming from the speaker from your computer right now, it's passing through the air, and the air is vibrating along the line that goes to your ear. Okay, now that doesn't mean that the the air particles that are right next to your speaker are actually traveling all the way over to your ear and hitting against your eardrum. They move in a little pocket back and forth, which causes the next air particle to vibrate, which causes the next air particle to vibrate, and it's just like a domino effect all the way up to your ear. Okay? So if I were to be across the room and yell at you, that doesn't mean the air from inside my mouth travels all the way across the room and hits your eardrum. If that were true, only one person would hear me. Okay? So, please try and get that straight. You might need to look up a little more about it on Google, but just remember, you got to be careful about what sources you credit as you guys are learning in civics and government. Okay, and just real quick, I just talked about this. It's just a little more of a formal definition of it, and you can see by producing a transverse wave, you have to move the medium up and down in order to get the wave to move from left to right. Okay, that's a key aspect of a transverse wave. Okay, and again, example, electromagnetic waves like light are produced by a vibrating electron. Now, we'll get into much more specifics of that when I see you again. That's something I really want to talk about with you guys in person. And longitudinal waves, as I said, move in the direction, okay, that the wave is traveling. You see the wave moving to the right, and you also see the little rings in the slinky moving back and forth, left to right, parallel to it. Okay, so those are so out of this video you should understand what the types of waves are and what forms they take. Now there is a third form that's called a surface wave, which is a combination of both of them. Now we're not going to get into those, okay, because that's a little more complicated and we don't want to spend the whole rest of the year talking about waves. We could spend years talking about waves because it's a really interesting subject, but we just don't have the time for it. So you really need to understand the comparison between electromagnetic and mechanical waves, and you also need to understand the comparison between transverse and longitudinal. Okay, so those two things you should be able to compare, and that does not mean just being able to rattle off a one-sentence definition like you see on the screen right now. You need to be able to actually compare them deeply. Okay, their velocities, their frequencies, where would you find them? Where wouldn't you find them? How are they different? All that stuff. Now we'll get there. I'm not saying you have to do that after this little video, but you need to start filling in more blanks. If you have questions about this, you need to write them down. You need to start looking them up. You need to be advocating your own work right now. Okay? Now I'm going to be back soon, and we'll pick this up, and I'll answer any questions you have and help you with it. But you need to get this rolling on your own, because I'm going to expect you to be able to compare to some degree longitudinal and transverse, and then you should be able to compare mechanical and electromagnetic. Okay? So I'm sorry I'm out, guys. I'll be back soon, and if I'm not back soon, I'll make sure that I have more of these videos to help you. That way you can always go back and look at them if you need more help, and it'll also give you an idea of what questions you might want to ask.